Good morning, good afternoon, and good evening, everyone. This is Terry Schlosser with the Rackspace Private Cloud marketing team. I'd like to welcome you to today's webinar, Rackspace Private Cloud powered by OpenStack Kilo. This is our version 11.1 webinar. Today, we are joined by Philip Williams, our principal architect for the RPC powered by OpenStack product. Phil, this is his first webinar, and he joined this is his first webinar with Rackspace, so I just want to do a quick introduction since he hasn't been one of our regular speakers. Phil joined Rackspace in 2011, previously working for folks like Yahoo and EMC in storage-related roles. He's been responsible for designing and deploying infrastructure to support many different industry sectors, including Rackspace's multi-tenant environments. He's currently responsible for the integration of enterprise hardware and open source software-defined storage with our OpenStack-powered private cloud offering. And so with that, I would like to hand it over to Phil for him to get started.
Thank you very much, Terry, and thank you to everybody who's joined today. I'm really pleased everyone can join so I can talk a little bit about some of the new features within our 11.1 release. Our team's worked rather hard to get a bunch of additional storage solutions supported with our products, and also to add functionality to some of the platforms that we already supported. I'd also just like to remind everybody that the webinar is being recorded, so if you do want to go back and watch the replay, that'll be available later. So firstly, I just want to do a quick recap. OpenStack is an open source software, a series of software projects used to build public, private, and hybrid clouds. Originally, it was conceived by ourselves, Rackspace, along with NASA back in 2010, with the Swift and the Nova projects, respectively. Over time, that moved into the OpenStack Foundation, and now has tens of thousands of contributors the world over. OpenStack itself is not a product. It's a collection of projects. Each of those projects has different goals and different focus. There are 6 core projects within OpenStack and then 13 optional projects. This makes deploying an OpenStack cloud not really straightforward. If we take Nova, for example, there are around 700 unique configurable attributes there. There are 38 Neutron plugins and over 40 different Cinder drivers. The combination of these would could quite easily lead to a near infinite number of unique clouds or deployments, depending on your viewpoint. And that's where Rackspace comes in. As projects reach maturity within OpenStack, our engineers and architects look at those projects, we evaluate them. We look at how consistently they can be deployed. Are they stable? Do those features and functionality that they provide, do they scale? And importantly, can we provide a fanatical support experience around them? Whilst not every project or feature has reached this level of maturity, we follow those that haven't yet. We keep an eye on what's going on and how widely used they are across the community. And over time, we're able to introduce newer projects within our product. Rackspace Private Cloud is for every business that wants the power of the cloud, along with the security and control of a dedicated environment. The key here, by using Rackspace, the key is that we take away some of the effort and expense required to manage those environments. We use standard open source software as it was intended to be delivered. We don't fork any of the OpenStack code. We don't apply any proprietary wrappers around that code. This approach offers our customers choice and freedom without the perils of vendor lock-in. Once code is forked, it can be rather difficult to get back onto that mainstream code. Our private cloud, powered by OpenStack, provides world-class performance, scalability, and availability. And we have a number of guarantees that we provide within our deployment methodology, which I'll talk about a little bit later on. We offer the flexibility to deploy your cloud either within our data center with our supported hardware or within your own data center and your own hardware. There's obviously some slight nuances between those two environments, but essentially it's the same software doing the same thing. We provide our legendary fanatical support. Rackspace is known the world over for our support. We have teams of specialists who proactively monitor and maintain the health of your cloud, and they're always available 24/7. The expertise of our engineers is certified by Rackspace as the company that co-founded OpenStack and operates the world's largest OpenStack public cloud. We can also provide DevOps services to help you unlock the power of your cloud through automation. And finally, within a Rackspace data center, we can provide a hybrid approach. We use another product of ours known as Rack Connect, which allows you to have a private connection into the Rackspace public cloud, which gives you the ability and the flexibility to run the right workloads in the right places, depending on changing workloads and changing demand. Rackspace Private Cloud, powered by OpenStack, gives customers all the power of cloud without the pain of running it, so that you can focus on your core business. So now that I've just done that sort of quick overview of OpenStack and Rackspace Private Cloud powered by OpenStack, let's talk a little bit more about what's new within our 11.1 release. So first up, we've added some functionality into our Swift deployments. In addition to our current single site or single physical region, we've added support for multiple dispersed data centers or dispersed regions. This is to enable things like disaster recovery. Next up, we have added support for Soph, specifically around RBD, to give us block-based storage support for Nova ephemeral disks, for Cinder and for Glance. Third up, we have added support for the market leader EMC's VNX2 storage array. That will be available both in a unified or a block-only configuration. And again, that provides support for Nova ephemeral, Cinder, and Glance. And finally, we're also adding support in this release for Rackspace integrated systems of storage. So that's taking our expertise within open compute hardware and providing that in a building block fashion that can be deployed within Rackspace or customer data centers. So let's look at Multiregion Swift in a little bit more detail. So essentially what we have here is a fairly vanilla deployment of Swift. Instead, it's stretched across 2 physical locations. Those locations could be the same campus, different halls within the same data center. They could be in different countries, or they could even be different continents. Objects are written into the primary region. So in this case, I have DC1 over on the left side. Those objects are then replicated within the regions inside that one data center. And then asynchronously, objects replicated across the WAN link to data center 2. And then depending on the requirements for durability, multiple copies would then be made locally there. The proxy nodes, so they're the ones called out as Swift proxies up at the top. They can read from both the local and the remote regions. So if we were to lose the storage nodes within, say, region 1, or across the entirety of DC1, we could actually read the data from DC2 automatically. We recommend using priorities or localized priorities to avoid those slower and more latent reads, especially when the local storage nodes are available. The one caveat with this kind of deployment at the moment, Keystone, which we use for authentication, would still be a single instance. So if Keystone was also lost along with the entirety of, say, DC1, whilst the data would be safe for disaster recovery purposes within data center 2, we wouldn't be able to provide sort of immediate failover or a business continuity type solution to actually access that data. Some level of manual intervention would be required. One other key point to consider, and this is where Rackspace's engineers would help size this component rather specifically, is the network infrastructure between the two sites. Not only the pipe itself, but also the devices on the end of that pipe. So if we're using something like a site-to-site VPN to get between the two data centers, we can be pushing quite a significant amount of traffic depending on the incoming write workload. So we need to be able to model essentially what's coming into the Swift cluster in the primary data center, and then how much data would need to stream to the second site. This is important because whilst Swift being asynchronous, things like peaks and troughs get smoothed out by that nature. But if we have a fairly sustained write workload and the pipe between the two sites is just not big enough, we could get into a situation where we're never able to get DC2 consistent with DC1. So moving on to Soph, this is a piece of software that we've been asked for a long time to add to our toolkit. Our primary goal with Soph was to provide a HA Cinder backend. Obviously, we've already offered things like NetApp in the past, but sort of fitting with the mantra of OpenStack and open source first, Soph is the perfect fit. It's become rather mature over the last few years. It performs well. We're not saying that Soph is a complete replacement for native Cinder. We're still supporting native Cinder, still deploying it. It depends on a customer's use case. Within a Rackspace data center, we have some standardized storage node offerings. One is a capacity-based solution. One is a performance-based solution. I'll talk about those in a little bit more detail on the next slide. Soph allows us to expand the storage available on an instance on the fly. We can add additional Cinder volumes via the Soph RBD protocol. We can also reduce the requirements for localized compute node storage by booting instances with ephemeral disks hosted on the Soph cluster. So instead of having an instance's local disk being on very localized disks within a compute node, we can use cross-network storage like you would in a sort of a typical SAN environment. The disks for the ephemeral disks can also be created at boot time automatically just by taking a snapshot of an image that's already stored on the Soph cluster. So that helps us to reduce boot times further. Instead of having to copy that image in its entirety over to a compute node, we can almost instantaneously start accessing that within the Soph cluster. Soph also gives us the ability to complete rather rapidly live migrations of running instances. There's essentially no downtime. If you were pinging an instance while it's being moved, you may see a couple of packets lost. But in essence, the instance is moved completely live between physical nodes. And this is a great thing for carrying out maintenance work. Instead of having to shut down a bunch of instances and then restart them all again on different compute nodes, we can do a live migrate, essentially evacuate everything from a compute node, do whatever work's needed on that hardware, and then shuffle things around again to make use of that hardware after the maintenance. As I mentioned before, if we have instance images stored on the Soph cluster, we can have rapid boot times. So that the reason for that is that we can use the Soph cluster as the glance image store as well. We can also create snapshots of running instances. Whilst we can't back up a running instance per se. We essentially take a snapshot first, and then we use that snapshot as a point-in-time copy. Like anything storage, that is essentially a crash-consistent point in time. There's no integration yet to allow us to quiesce I/O, like you would find in, say, sort of an enterprise IT application that would tie into a typical storage array from, say, EMC. That probably will come over time. And finally, we have enabled monitoring using the Rackspace monitoring as a service tool. So in the same way that we monitor the elements of the environment, we feed similar health metrics back to the Rackspace monitoring as a service cloud to keep an eye on the health of the Ceph cluster. A couple of points to note with the Ceph support. So right now, we're not providing support around CephFS. CephFS is essentially file system as a service, or a POSIX file system. That part of the Ceph project is still not widely used, and there are some scaling issues with it. And similarly, with the Rados Gateway, whilst we don't think it's very far away, we intend to support it at some point. Right now, we're not comfortable supporting the Rados Gateway within the Rackspace private cloud powered by OpenStack product. You may find it supported elsewhere. So on to a brief sort of overview of the architecture itself. We use the RPC control plane. I'm actually going to cover that a little bit later on, just as a refresh. So that's we deploy 4 servers to run all of the various OpenStack services. Because of the containerized nature of those services, we can add some more. So for Ceph, we reuse those pieces of hardware to run the Ceph monitor services. For Ceph, and in all honesty, all things storage, we recommend and mandate 10 gig Ethernet. It's theoretically possible to use 1 gig Ethernet, but we feel that the performance provided doesn't lead to a good experience. And the Ceph nodes themselves, they're dual processor dedicated servers. The processors we're using are a fairly sort of mid to high end Haswell processor. We use a couple of drives in there for the operating system for logging those kind of tasks. We load both of those servers with a couple of 10 gig NICs so that we can have a back end replication 20 gig bond, and also a 20 gig bond for client access. So for when instances are accessing the storage array, each node has up to 20 gig of bandwidth available. You can think of each of the storage nodes as fairly general purpose. Depending on whether you need a performance offering or a capacity offering, we just basically swap out the disks required. Our performance offering is full SSD. We dedicate 4 of those SSDs to be journals, and the remaining 20 of those SSDs to be OSDs. And then in our capacity offering, we have, again, 4 SSDs as journals and 20 nearline SAS disks to provide that capacity offering. Just want to add a little bit more detail around the tasks that the journals and the OSDs provide. The journals essentially act like a buffer. They capture the incoming writes to the Ceph cluster, and the OSDs, you could consider those as like a persistent object store. The combination of the journal and the OSD, they're controlled by what's known as the OSD daemon, and that daemon makes sure that data is written synchronously to multiple locations within the cluster. So when I write a block of data to Ceph cluster node 1, Depending on the protection policy that I have in place for that particular pool, multiple copies will be written to other physical nodes. We will never replicate data within the same physical node, but we will spread things out across the cluster automatically. Within the standard storage nodes available within a Rackspace data center, we use a 1:5 journal to object storage device ratio. We've done this to try and balance cost, performance, and reliability. It's always difficult to try and balance all three of those. And each of those journals, we actually partition them up to provide an individual area for each of the OSDs. That adds a little bit of a increased sort of failure domain for an OSD. If the journal was to become corrupted for a single OSD, we would obviously only lose the contents of the single OSD. Data in that scenario is still safe because it's replicated elsewhere in the cluster. We can just rebuild that single OSD. Moving on to providing some support for some enterprise storage. Previously, we've provided support for NetApp's FAS, sort of mid to high-end storage arrays. Within Rackspace, we also have, for a long time, supported EMC storage arrays, both VNX, also VMAX. We've added into RPC by OpenStack support for the VNX2. This is a very multi-purpose type storage array. It's available in a couple of different configurations. There's Unified, which provides you with NFS, CIFS, and also block storage. And it's also available in a block storage only offering. The real goal here is to provide something that provides support for a storage vendor that people trust. One thing I've come across working in the storage industry for the last decade is that the most critical thing to any business is customer data. And if a business doesn't have access to its data, there's essentially no business. And whilst some customers are slightly more cutting edge and they will look at open source type storage technologies, there are also those that, again, treat that data like it's gold, and they want to use a platform that's known, is trusted, comes with its own SLAs. So in this case, the VNX2 is a highly available, fully redundant mid-range storage array. It's very flexible. We can configure them in various different ways. We can enable things like storage tiering, which automatically moves data between different types of disks. We have enabled the ability to add cinder volumes to instances using iSCSI. We already have environments with 10 gig Ethernet, so we'll be using that one standard network. Also enables live migration, very, very similar to Soph. And we can also use part of the storage array to store glance images. In this case, we use a share. Again, it's over 10 gig Ethernet, so it's very performant. And of course, being a enterprise storage array, things like snapshots and clones are available, and we can use those to create backups of running instances. Again, as I mentioned with Soph, they are still only crash consistent, but that's a great way of being able to recover after any kind of logical failure. One thing to note here, well, actually two things to note here. We're not enabling support for Fibre Channel at the moment, and whenever we would deploy one of these arrays within a Rackspace premise or Rackspace data center, we would actually bring in a member of our dedicated storage team, and they would actually work with you, the customer, our Rackspace private cloud engineers, to understand the workloads and understand the right fit to make sure the array is designed to suit perfectly. And just a little overview of the sort of networking requirements. So again, we have a control plane in place. Obviously, the Cinder volume service would run on that control plane. Again, as with Soph, we would mandate redundant 10 gig Ethernet. When storage disappears, it's not so much like a normal internet connection going down or a normal LAN connection going down. Operations tend to continue after that. With storage, there tends to be a rather long period of time rebuilding indexes and recovering from corruption and those kinds of things. As I mentioned before, the VNX is available in a block-only configuration, so that provides services for Cinder, or in a unified configuration, so again provides services for Cinder and also Glance via NFS. As I also mentioned, the Rackspace storage specialists, or the storage engineers, would be very heavily involved to make sure that this kind of platform is designed to suit perfectly. And the final new feature that we're announcing within this release is support for Rackspace integrated systems for storage. So using our Open Compute project expertise, OCP was a series of projects started by Facebook, adopted by a number of other people across the industry. We've been making use of it within our public cloud. We've now released a rack-based storage hardware solution, which is compliant with the OCP spec version 3. We deliver this as a fully tested rack-level solution. It's fully integrated at the time of manufacture, which means we have much faster deployment times once those racks are on site. It's very much a case of add power, add network uplink. We can start making use of that gear. We can make use of Rackspace integrated systems for storage, for things like native Cinder, so using LVM over iSCSI, along with Swift and Soph in the future. Let's take a look at one of the cabinets in a little bit more detail. So for the storage-based solution, we have 24 servers within the cabinet. Each one of those has 2 hex-core processors, along with 64 gig of memory. Within the direct attached JBOD, there are 14 6 terabyte 7.5K SATA drives. We typically see those drives as being protected by RAID 10, so we see 42 terabytes per JBOD in a protected configuration. So overall, you see around half petabyte within the entire cabinet, or around a petabyte raw. Each cabinet has 2 top-of-rack switches with 40 gig of HA bonded uplink, and the servers themselves have 2 10 gig HA bonded network interfaces. And these are available. These cabinets, or these building blocks, as we like to refer to them, are available for private cloud use within both Rackspace US and UK. I just wanted to end by, well, not really end. I just wanted to go over the minimum requirements. As I've mentioned, the control plane a few times. So for version 11, our minimum requirements are HA firewalls along with HA load balancers, and 4 dual processor servers. So they provide us with the control plane for all the OpenStack services, as well as a logging server, so that we have a centralized logging resource. As a minimum footprint, we mandate 2 compute nodes, and then as a bare minimum, we can use the Cloud Files public cloud service for Glance image storage. At Rackspace, we have specific hardware models which fit into these groups, but these are the sort of loose specifications. We also recommend redundant networking. I've talked about that before, and for these kind of environments, 1 gig and 10 gig is perfectly acceptable. Obviously, the performance of 10 gig is greater. For heavy storage use, my recommendation would be to go to the 10 gig direction. And because of the way that we've designed the architecture, so all the OpenStack services are within LXC containers, we're able to carry out in-place upgrades. So we can move from Juno to Kilo to eventually Liberty and beyond with minimal disruption to cloud consumption. And the RPC powered by OpenStack offering is quite flexible. Whilst we mandate a particular operating system and a particular type of hypervisor, in terms of hardware within your own premises, you can make use of anything that is certified by Ubuntu. Storage, we're slightly more prescriptive. We have support for Swift. We also have reference architectures for Swift, if that's something that would be of interest to anybody, please let us know. We support drivers for NetApp, EMC, Soph, and native Cinder. There are others in the works, and we can consider others if you say already have a type of storage array that you already want to use. From a networking point of view, we originally were using OVS. We actually moved to using the ML2 plugin and Linux Bridge agents to provide a more stable environment. And that gives us a reasonable amount of flexibility in terms of provider and tenant networks and how we can count things up. And obviously we support GLANS and all of the various formats of virtual machine images. If we're using Soph and we want to make use of some of the ephemeral boot options in the way that we can snapshot those images, we would need to look at the formats specifically and make sure that we either convert them to a compatible format so that we can snapshot them, or we don't lose any functionality, we just don't gain that additional rapid boot time. I just wanted to talk a little bit around fanatical support, and it's the mantra of Rackspace, and I think what we're famous for. Rackspace private cloud powered by OpenStack is no different to any of our other products or any of our other services, in that we can provide this level of support around OpenStack in our premise, in your premise. Customers can benefit from a dedicated support team and 24/7 monitoring and maintenance. If a customer believes it's necessary, if they have quite complex requirements, we can also look optionally to assign a dedicated OpenStack engineer to the account. And then when we build, or when an environment is built using our reference architecture, those various SLA guarantees apply. So for the OpenStack API, we provide a 4.9 uptime, along with a 15-minute live response time to emergency tickets. And within a Rackspace data center, we're obviously supporting the hardware as well and that underlying infrastructure. So we're able to provide our 100% network uptime guarantee, along with 100% availability for the critical data center related infrastructure systems. And also we have the ability to provide a 1-hour hardware replacement service as well. Our support is available in 2 flavors. We have escalation support, so we see that as almost like a transactional support request type environment, where a customer is very confident in managing the environment themselves, and occasionally they will have questions. They're already quite technical. With core support, that's very much the managed cloud almost cloud as a service type approach, and that introduces the 50-minute response times and the 4 nines API uptime. And almost finally, I just wanted to mention some of the customers that we already have using our software. And they receive our engineers expert support for their private clouds. Some of these are available as more detailed case studies as well. Got a link coming up where some of those case studies are available. And if you reach out to us directly, we can provide more information on those as well. As I just mentioned, further information, including case studies and technical documentation, can be found on our website. Our software is freely available from there, along with all the technical documentation to go with it. There's no licensing for making use of that software. And of course, please get in touch for any more sort of detailed inquiries, any questions around support of IBC powered by OpenStack. And finally, I'd just like to hand back to Terry to moderate a Q&A session. Terry, are you around?
Yes, I am. Thank you, Phil. I just would like to let everyone know that if you have a question, please go ahead and put it into the chat. I'll be asking Philip all of your questions as they come in. So the first question for you, Philip, is it necessary to reboot the machine in order to start a snapshot? Is the machine available during snapshotting? Copy on write?
Okay, so whenever you take a snapshot, there's no requirement to restart that virtual machine if the virtual machine is hosted either on a Soph cluster or on a VNX or a NetApp filer. As long as the underlying disk for that instance resides on a storage array, we can take a snapshot there. As I mentioned before, those snapshots are crash consistent only. If you want a fully consistent, known perfect golden copy, shut down the instance and then take the snapshot, that's the way to do it. But for most use cases, a crash consistent snapshot is a great way to make a backup of a running instance.
Okay. One other question. Why enable all these storage choices? Why not sort of just settle for one and then make that the default? Okay, so
within any kind of any decision, I guess, and specifically within technology and then in storage, there are different levels of maturity and different levels of use case or different ways of using storage. If we think about cloudy applications, they talk in objects, they talk to REST APIs. So Swift becomes a natural fit. If we think about an Oracle database, they typically talk in blocks to a local disk or to a storage array. So then Cinder becomes the sort of natural option. When we look at Cinder, we think about EMC as an option and NetApp as an option. They're two great enterprise storage arrays. People tend to have different affinities to them. And also thinking around block storage, we look at something like Soph. And whilst Soph is a maturing open source project, the confidence levels are still not quite there. So having that ability to use an enterprise storage array, or even an enterprise storage array that you already have on your data center floor, allows for reuse of that asset. There's so many reasons why you would do different things, and it's a difficult question to answer, but I think that what I'm trying to say is that choice is hard. And depending on the maturity of an application, or depending on the generation of an application, over time, deployment methodologies change and storage access changes. We're in that, again, in that evolution now where for many applications, we're moving to object. We're not having stateful connections to and from storage systems, not specifically thinking at a low level like in SCSI, but when we use a mobile phone and we upload a picture, they tend to reach clouds now, and they tend to use HTTPS over fairly flaky connections. SCSI could never do that. So it depends, which has always been the mantra of the storage person. The choice is great.
So just to summarize, we're trying to give our customers as many sort of choices as possible because they all have some sort of different use cases that they need to address.
Absolutely.
Okay. So one more question. In reference to our VNX support, can you tell us a little bit about the fiber channel connectivity and why we're only supporting Ethernet?
Okay, so if we go back to the overall architecture that I showed towards the end of the presentation, we see one type of network within that environment, and that's Ethernet. Traditionally, with storage, we have tended to build out a separate network to carry storage traffic. The network of choice has always been fiber channel. As Ethernet and fiber channel tend to tick-tock in speeds, so Ethernet will get a speed bump, and then 6 months later, fiber channel will get a speed bump, and we'll keep going in those kind of cycles. Ethernet and fiber channel are at throughputs that are pretty similar now. Okay, I know that fiber channel will get another tick later this year to get up to 32 gig, but they're again 40 gig Ethernet is becoming affordable. We've got to this point where we can make use of a single network to do all of the different things. We can use it for object storage, we can use it for management, we can use it for block storage, and we can apply things like QoS to keep those different types of traffic from impacting each other. They don't necessarily cause problems for each other anymore. I know in the past that was always a concern. Ethernet has become much more robust, and even some of the features from the fiber channel world are now starting to creep into the Ethernet world. So Ethernet's definitely matured to a point where we can use it as a single converged network. We don't have to manage two networks. We don't have to cable two networks. We don't have a second set of devices to look after, another set of interfaces to look after. It's a much more simple kind of environment. Okay, those are all the questions that we've gotten in so far. Thank you, everyone. There's been a lot of activity on the chat, and I've answered, some specific questions there as well. I would just like to thank Philip for presenting for us today. Your insight in storage is always very enlightening for myself, and I hope to everyone that joined today. If you do have any other questions, there's a link for our RPC sales team, or you can reach Philip at his handle on the front page. We will be sending an email, a thank you email, with a link to the replay of this session, so if you want to go back and reference it or share it with others. And that's all for today, so thank you. Have a great day, everyone.